So remember, 4.1 and 4.2 are going to be fair game for your exam. This is all about finding maxes and mins. So we talked about the first derivative test, which is essentially where we did this one full example down here. Remember, we find the derivative, we set it equal to 0, find if it's ever undefined. For us, undefined means we would have a denominator being 0. And then we have this kind of number line idea, and we have our kind of test points in each kind of piece of that number line. And then we find whether or not it's max or min from there. So that was the first derivative test. So we need to talk about the second derivative test really quick. And then we'll do a few more examples, and then we need to talk about something called inflection points. So let's get started. So we kind of got to scroll back up to the second derivative test. Well, let me scroll back up here really quick. So remember, this is all about finding extrema. So whenever we have to find extrema, even with the second derivative test that we're going to talk about right now, the thing that you always have to do first is find the derivative and find the critical points. And remember, the critical points are where the derivative is either 0 or undefined. So you would do that even if you're using the second derivative test. But then with the second derivative test, what you do is, so you have your critical point, suppose that P is a critical point. What you're going to do then is you're going to find the second derivative. And I don't think we've ever officially done one up to this point, but essentially you find the derivative and then reshare my screen. Yeah, you find the derivative and then just find the derivative of the derivative. That's how you would find the second derivative. What you do with the second derivative then is you're going to plug each critical point into the second derivative. Hopefully that worked, Merrick. I squeezed that in a little too much. Let me. Second derivative. To find out if it's positive or negative. Ooh, the lag is real. At least on my screen. Come on, you can do it. The lag is not what we need today, little computer. There we go. So you're going to plug each critical point into the second derivative and figure out whether it's positive or negative. If when you plug in that number, you get a positive number. So think about this, because I always need to kind of think about this because I always try to say it backwards. If the second derivative is positive, then you're concave up. So concave up, remember, you know, this is kind of like what our concave up options look like. So if it's concave up, let me try to share one more time to try to get rid of some of that lag. Sometimes resharing helps. So if we're concave up like a cup, that would mean that essentially that critical point would end up being that minimum. So we would have a local minimum there. Whereas if the second derivative is negative, that means we would be concave down. And essentially that critical point ends up being the maximum. So we would have a local maximum. Why it ends up being the min and the max, kind of just trust and believe me, but take those little tiny kind of drawings to be the way you should think about it. My one screen is lagging a lot again. And I don't know if yours are as laggy as mine, so I always like to try to wait until it's done, but it's being a jerk. Come on, you got this. Go, go, go. Yeah, Anastasia?
Wait, I'm confused. So when you're saying it's a local minimum or local maximum, is that a local minimum or maximum of the original function or of the second derivative function?
Of the original function.
Okay, thank you.
Yours is really laggy too. Yeah, so I'll try to, if there's ever a time where I'm moving on and yours still hasn't caught up yet, let me know. Mine's finally caught up, so hopefully yours has too. But always feel free to just yell at me in chat if things are lagging too much on your side. Now, the bad thing about the second derivative test is that if the second derivative is that point in, the test is inconclusive. And you have to use the first derivative test anyway. So that's kind of the sad thing about the second derivative test. Oh my lord, it doesn't register anything that I've written. That's funny. Except it's not funny because we're on a time crunch. Anyway. So the second derivative test is useful, honestly, a bit more in a different calculus class. But I know for sure that there's one question on your homework, and remember, that's been pushed back. I sent out an email about that the other day. I think it's also an announcement on Blackboard. Anyway. There's one question on your homework where it like gives you a critical point and it gives you the value of the second derivative there, and that's what you use to figure out if it's a max or a min. So sometimes it is kind of useful for other reasons. In general, the second derivative test, kind of two notes. If the second derivative is really gross to find, you probably then just don't want to use it. Just use the first derivative test. And again, sometimes it doesn't work, so you have to use the first derivative test anyway. Anastasia, is that a new question, or is your hand just still up?
No, sorry, I just forgot to take it down.
Okay, no problem. I thought it popped up again, so I just wanted to double check. So, well, the second derivative test, I would suggest not necessarily using a lot, because again, it doesn't necessarily work. It is something where yeah, I can share my screen again. Sometimes there are certain types of questions where it can force you to use it. There won't be any ones on the exam where you're forced to use the second derivative test, but they do exist in general. So what we're going to do now is we're going to use the second derivative test to confirm that this polynomial has a maximum at -2 and a minimum at 8. So I did reshare, so let me know if that didn't help, but hopefully it did. So we want to, now I'm going to do a bit more than this question is asking for, just for some review-based purposes. But anyway, so we would want the second derivative, but to get the second derivative, the first thing we need is the first derivative. So we need to find the derivative. So we get 3x squared minus 18x minus 48. And here's where I'm going to go a step above what this question is asking of me. Say I actually wanted to find the critical points. Say they weren't given to me. So they're kind of given to us here because we're told -2 and 8. But say we weren't told those and we needed to find them just for review purposes. What I would suggest doing is I always suggest pulling out common factors from all of these terms. So all of those terms are divisible by 3, so we could pluck it out. So you get x squared minus 6x minus 16, if I'm remembering correctly. So I forgot to pull out my notes with the actual answers on them. But anyway, and then if you wanted to set this equal to 0, what you would then do is you could factor this. You could also use the quadratic formula. And the quadratic formula can be helpful for some of these because there are some questions that you can't use by factoring. So to remind us of the quadratic formula, if you somehow have ax squared plus bx plus c, you would use the -b plus or minus the square root of b squared minus 4ac all over 2a. So again, this question wasn't asking us to do all this, but just for review purposes. But if I wanted to factor this, that's where I'm looking for numbers that multiply to -16 and add to -6, which would get me -8 and +2. So this would factor into x minus 8 and x plus 2. And remember, when we're finding critical points, that's where we set a derivative equal to 0. So if we were to set this entire thing equal to 0, we would essentially take those 3 pieces and set them equal to 0. So 3 equals 0, which never happens. X minus 8 equals 0, and x plus 2 equals 0. And that's essentially where they're getting the 8 and the -2 from. So again, wasn't needed for that question because we're already told the critical points. But if we needed to find them, that's of course how we would find them. And remember, well, maybe not remember, but if you use the quadratic formula just gets you the answers. So if you use the quadratic formula on that, you would get 8 and -2. But anyway, here what we're actually asked to do is to use the second derivative. So we would need the second derivative. So we would take the first derivative and then take the derivative of that. So we would get 6x minus 18 And now with the second derivative test, we take our critical points, that 8 and that -2, and plug it into this second derivative. So we want to find f prime of -2 and f double prime, I think I said prime on the first one, f double prime of -2 and f double prime of 8. So 6 times -2 minus 18 and 6 times 8 minus 18. When we plug in -2, we're going to get -30, which is, -30, which is of course less than 0. Since -30 is negative, that would mean that we're concave down there. So if we're concave down, that would mean that this is a local max, which we were just triple checking. We are kind of told that it's a local max, but we wanted to double check their work. And then if we plugged in 8, we would end up with +30, which is just a coincidence that they're both 30s, which is positive, so we would be concave up, so that would end up being a local min. So that's how the second derivative test works, is you find the second derivative test, so you find the second derivative, you take the critical points that you find and plug them into the second derivative to find if it's positive or negative. But again, sometimes, every once in a while, this does not work. So you do want to be kind of careful about it. Questions, concerns on that one? And again, you are never, for me, at least not on this exam, maybe for the final, but I'll let you know, probably not. You're not really ever forced to use the second derivative. On your homework, there is at least one of them that does. But it's also kind of a sneaky second derivative test. But anyway, so I'm not seeing any questions, and I've waited for a couple of seconds so people can catch up. I'll wait like 5 more seconds. Cool. So we already did that example, so moving on. So let's do one more. Well, one more for right now. Do a couple more later if we have time. Use whichever derivative test you like to find the local minimum and maximum, well, local minima and maxima of this function here. I'm probably going to default to the first derivative test, not only because it's probably what most of you are going to use anyway, but also in this case, let's remind ourselves what that looks like because we haven't done it in a while. So we want to find the local maxes and mins. So the first thing is find the critical points. So for the critical points, we need the derivative. So really the first thing is to find the derivative. And we have a chain rule here because we essentially have something to a power. So chain rule, since we have something to a power, we're going to use the power rule. Bring the power down, subtract 1 from the power. But the chain rule says to leave that inside piece alone at first. And then we have to multiply by the derivative of the inside, so the derivative of the x squared minus 4, which will get us 2x minus 0, so I'm not going to write the minus 0. While it doesn't help a ton, I'm going to rewrite that as 14x, x squared minus 4. Sometimes the simplification really helps out here. This one's kind of like, you can if you want to. It's not the end of the world if you don't simplify that. But the one we did the other day, it was really helpful to do a bit of simplification first. But anyway, we found the derivative, and now we need to find our critical points. So remember, there's 2 cases for that, whether the derivative is 0 or undefined. So we need to set the derivative equal to 0, and we need to ask ourselves, is the derivative ever undefined? Now remember, for a function to be undefined, there's a lot of different things that can happen, but in terms of our class, the only thing we have to worry about is if there's a denominator, we would have to set it equal to 0. There's no denominators here. So this is going to be never undefined, so we don't need to worry about that. The only thing that changes if there was a denominator and we set it equal to 0 and we found a point is that we would have more points on our number line. It doesn't change anything else besides that. All it does is add more numbers onto our number line. But we do need to set this derivative equal to 0. Now notice that this derivative is kind of made up of two things that are multiplied together. The only way you can multiply things together and get 0 is if one of those things must have been 0. So we can essentially break this up and take both of those pieces and set the pieces equal to 0. Ooh, the lag. Ooh, the lag. There we go. So the 14x equals 0 would give us that x equals 0 if you divide both sides by 14. And then for the other piece, we would want to sixth root on both sides, but the sixth root of 0 is 0, so that's nice. Add 4 to both sides. Square root. Remember, when you square root something, you get a plus minus. So we would get plus minus 2 from that piece. So that means that our critical points are 0 and positive and negative 2. And remember, these questions get a little long, so sorry. So once you have your critical points, you plot them on a number line. So we've got negative 2, 0, and 2. Make sure they do get put in order. And this is where we choose our test points. So remember, now we want to essentially choose a point in each kind of section. And now the reason we're doing that is because the only points where a function could have a max or a min is, so if you think about, just trying to back up why this is what we're doing. If you think about where a max is, it's going to have a tangent line with a slope of 0. Same thing at a min. So that's why we find the derivative and set it equal to 0, because that's the possible points where we could have a max or a min. Now there are also some other points on certain functions where the tangent line could also have a slope of 0. So that's why we need to do this little number line, and we need to kind of figure out what the sign of the derivative is in each case. So we got to pick some numbers. Something less than negative 2, I don't know, negative 3. Something between negative 2 and 0, negative 1. Something between 0 and 2, 1. Something greater than 2, why not 3? You get to pick whatever number you want, as long as it's in that section. You can pick any number, and as long as you've done everything else correctly, it should work out. But anyway, so now we're going to take all of those test points and, plug them into the derivative. Now I'm going to show you a type of shortcut. You don't have to do the shortcut. You can do the long way always, but I'll show you the shortcut too. Let me do one thing real quick. There we go. So a shortcut, since we don't actually care about what the number is, you can kind of think about what, what's the word I want? What the sign would be in each one of these cases. So say I plugged in negative 3, and say I'm thinking about it in terms of this 14x times x squared minus 4 to the 6th. If you plugged in negative 3, that 14x would turn out to be some kind of negative number. And then if you plug in negative 3 into the x squared minus 4, you're going to end up with 9 minus 4, so 5 to the 6th power. Well, that's going to be a positive number. So this is going to end up being a positive number. If you don't like that shortcut way, or if you can't figure it out by the time you need to, what you can do is just figure out what the number is. Plug in negative 3 to that derivative, and what's the number? It turns out to be, that's not, what have I done? Oh my God, a negative times a positive is a negative. Sorry. So the result is negative 6. Oh, that's a small number. That says 6 times 10 to the 5th. So no wait, that would be a large number. 14 times negative 3. One moment, please. I tried to do it a fancy way and it didn't like it. This would be negative 656250. Essentially, the point is it's a negative number. We don't really care what the number is. We just care that it's negative. So when I plugged in a negative 3, I get a negative. If I plug in negative 1, the 14x is going to turn out to be negative. that inside piece is going to turn out to be essentially -3 to the 6th power, but anything to a positive power, sorry, anything to a even power is positive. So we would get a negative here. Also, if you just found out the value, it would be -10,206. So we get a negative when we plug in -1. You don't have to do both of these ways. You don't have to do the sign and the actual number. I'm just doing both ways because different people might like different things. If we plug in +1, the 14x would turn out to be positive, and the -3 to the 6th would turn out to be positive. Positive times a positive is positive. Or you can just find out that it's equal to 10,206. So we get a positive value when we plug in 1. We plugged in +3, the 14 times 3 would be a positive number. I don't know what it is, but I know it's positive. And then we would have essentially 5 to the 6th power in that second piece, which would be positive. Positive times positive is positive. Or you can just plug in the number and find out that it's 656,250, which is positive. So I know it's been a while since we've talked about this, but I also mentioned that with the first derivative test, I like to draw little like line segments to remind me about what the actual function would be doing at these intervals. So remember, if the first derivative is negative, then the original function is decreasing. So let me draw like 2 little decreasing pieces in that first 2. And then if this derivative is positive, then I'm increasing. Let me draw like 2 little increasing pieces for that. So the only time that we're going to have extrema is when the derivative changes sign. So notice at -2 and +2, it doesn't change sign at all. It's negative to negative and then positive to positive. So those don't turn out to be extrema, which is why we have to do this sign chart, because sometimes your critical points aren't actually extrema. But at 0, it changed from negative to positive. And I think that's why I like to draw these little lines, because I think it makes visual sense that that turns out to be a min, because your original function goes from decreasing to increasing. So we would have a local minimum at x equals 0. And I'll even write no local max just to clarify that we don't have a local max here because there's no other place where the derivative changes sign. Questions? Let me clear that obnoxious thing up on the side. Any questions or concerns about that one? I'll wait a couple seconds in case anyone needs to catch up, or if anyone's typing a question, and then we'll move on to the next one. All right. So we'll come back to another one like this in a minute. But we're going to change gears just the tiniest bit for a second. And look at this one, which is we don't actually have an equation here now, we just have a graph. So say the value of some investment at time t is given by s of t, and the rate of change s prime is given in the following graph. So note, we have the graph of s prime, not regular s. So we have the graph of the derivative. We want to know what the critical points of the original function s are. So remember, we defined it a while back, but critical points are where the derivative is 0 or undefined. Since this graph of this derivative is, it's smooth and there's no like breaks in it or anything, essentially any graph we'll ever look at, since there's nothing weird going on there, that's never going to be undefined. So we just care about where it's equal to 0. So where is this derivative equal to 0? It's got a 0 here, here, and here. So we have that the critical points are going to be at 1, 4, and 6. And I'll even write since that's where the derivative equals 0 to remind us, that that is why those are the critical points. So now we want to identify whether these critical points are maximums, minimums, or neither of the original function. Oh, camera froze. No camera. Come back, no camera. Anyway, so let's start at t equals 1. And, well, hold on one second. Let me just write all these out. Let me scroll back up real quick. Back to, where is it? Right here. Way back when we were talking about the first derivative test and kind of what we were just using in that last example. So we're only going to have maxes and mins at where the derivative changes sign, and it does depend on how it changes sign. So if the derivative changes from negative to positive, we have a min. And if it changed from positive to negative, we have a max. So that's kind of what we want to look at here, is we want to look at where the derivative is. Is it positive or is it negative, and how does it change at that point? So if we look at t equals 1, to the left of that point, the derivative is positive. It's above the t-axis. And to the right of that point, it's also positive. It's still above the t-axis. So this one at t equals 1 would be neither, because s prime of t stays positive. It just kind of like touches the x-axis, but then pops back up. So it doesn't change from positive to negative or vice versa. So it's not a max or a min. It would be neither. Gonna wait for the lag. Lag, lag, lag. Could create a lag song, but I won't. Oh my goodness, come on. You got this, computer. Thank you. Again, some of yours are probably not lagging at all and you think I'm just insane, but I swear to God, one of my computers is lagging. All right, so at t equals 4, to the left of 4, the derivative is positive, it's above the t-axis, and then to the right of 4, it's below the t-axis. So since the derivative there changes from positive to negative, so let me try to it's positive to the left and negative to the right. So that would mean that the original function went from increasing to decreasing. So we would have a max there. So t equals 4 is going to be a max, since s prime of t changes from positive to negative. And then at 6, to the left of 6, it's below the t-axis, and then to the right of 6, it's above the t-axis. So essentially, the derivative changes from negative to positive, so the original changes from decreasing to increasing, so t equals 6 must be a min. S prime of t changes from negative to positive. So even though we didn't have a function, we didn't have, any sort of equation at all, we could still figure out if it was a max or min just based off of this derivative graph and how it changes, whether it changes sign or not. Questions, concerns on that? Okay. You know what, let me just I'll put this up here. Positive, just to make it a bit more full. All right, so then there's one last kind of idea we have to present for 4.2, and then we're done 4.2, and we'll just do another example or two of kind of a full problem. So hopefully you'll have that done. I'm going to scroll down, get this last bit. So a point at which a function changes concavity is called an inflection point. To test if a point is an inflection point, you must check if the second derivative changes sign. Does it change from positive to negative or vice versa? How we're going to do that is we're going to use a sign chart very similar to the first derivative test. But it's going to be with this second derivative instead. Please do not confuse this with the second derivative test. So the second derivative test is for extrema, and what we're about to do now is for these new things called inflection points. But essentially what we're going to be doing is essentially the same thing we do for the first derivative. With the first derivative test, we're going to find the second derivative. We're going to set the second derivative equal to 0. We're going to plot those points on a number line and plug test points into the second derivative. It's like the exact same thing, but just with the second derivative instead of the first derivative. So let's do one. Find the inflection points x cubed minus x. So if we need the second derivative, we need the first derivative first. So we'll get 3x squared minus 1. And then we need to take the derivative. So it's the derivative of 3x squared. That'll be 6x. Derivative of 1 is 0. So our second derivative is just 6x. Since we want to find where the second derivative, okay, so actually maybe I should babble a little bit more before we do this. Why is this why we're doing this? So, sorry, I forgot that was a mic. Didn't mean to blow at it. So an inflection point is where the function changes concavity. But remember, we have this relationship between the original function and its concavity, concave up versus concave down, and the second derivative being positive or negative. And that's essentially what we're doing here. We want to find where the second derivative changes sign, which is essentially what we're doing with the first derivative test with the first derivative. So we want to find where the second derivative is 0, and then use that number line to figure out whether it's positive or negative in each piece. So we found the second derivative, so let's set it equal to 0. We also, I should be clear, need to make sure that the second derivative is never undefined. We also need to do that here as well. There's no denominator, so this is never undefined. We very rarely will encounter a question in our class where it is undefined, but we do need to consider it. And so when we set it equal to 0, we get x equals 0. So that is kind of, I can't call it a critical point because that's not what it is, but that's kind of the idea, is that we found that point that makes that second derivative equal to 0. We plop that guy on a number line. Right, so Sydney, if it's undefined, so different color so we know that this isn't real. So say there was a denominator and I got that the denominator being 0 gave me that x is 1 for giggles. All that would do is make me plop a 1 on my number line, and then I'd have more things to consider. That's all you do with it, is it just gives you another point to put on your number line. That's the only thing you have to do with it. So it doesn't really change the problem a lot. It just gives you extra things to tack onto your number line. Now, with these little number charts, I like to label them with the derivative that they're working with. So I like to label this as a second derivative, because you'll see in a second that sometimes we have questions where you have to use both. So now we need to pick our test points. So something less than 0. I'm going to go stupid and go -10 and +10, just to prove that it doesn't matter what point you pick. You can go a little weird and pick some larger numbers if you want. So I'm going to pick -10 and +10 because I can. So I'm going to plug those into the second derivative. We would get -60 and +60 respectively, which would be less than 0 and greater than 0 respectively. Just like with the first derivative test, you don't really care what the number is, you just care about the sign. So when I plugged in -10, I got a negative, and then I got a positive when I plugged in +10. Now, sometimes I do this, sometimes I don't. So with the first derivative test, I like to draw those little line segments. You don't want to do that here because this is the second derivative, so it has nothing to do about increasing or decreasing. But if you want to just put something to kind of, maybe you really, really want to put something underneath of it because you did it for the first derivative, sometimes I'll just remind myself what that means about the concavity. So concave down in that first piece and concave up in the second piece. That's not as helpful as the little line segments, so sometimes I don't put them. But if you really want to have like that similar step to the first derivative test, that's what I would do. Anyway. And so, since the second derivative changes sign there, we have an inflection point. So we would have an inflection point at x equals. The nice thing about inflection points is you don't have to care how it changes. So with maxes or mins, it depended whether it changed from negative to positive or vice versa, whether it was going to be a max or it was going to be a min. Here with inflection points, it doesn't matter as long as it changes sign. So it doesn't have to be a specific kind of direction, if you will. It just has to change sign at all, and that will make it a inflection point. Questions, concerns on that? 3:30. Okay. Okay. I'm not seeing any. All right. What was that? Okay. All right. So, technically, there's two more examples that we have, and they're kind of like the full questions, extrema and inflection points. I'm going to do the first one. I don't know if we'll have time for the second one, and I also want to leave a tiny bit of time in case people had any questions. So I'm going to do this one fully. If we have time, if there's no other questions, I'll do the other one. But after this one, I'll kind of open up in case anybody has any questions in general about the exam. But let's do this one because this is kind of a full question of this type. This one will get, it's a little long. So bear with me, these do get a little tedious and a little lengthy, but I want to split it up a little bit, kind of like 2/3 on one side and 1/3 on the other, because we're going to have a lot of work to do. But, so we want to find all extrema and inflection points for this function. So we're essentially going to find the first derivative, do the first derivative test, and then find the second derivative and do the second derivative number line. You could do the second derivative test here if you wanted. Wait, is this one of the ones that is inconclusive? No, I think that's the next one. Anyway, but I'll talk about that when we get there. So for extrema, first thing you do is always find the derivative, find the critical point. So we need the derivative. Now note that this is going to be a product rule. So let me kind of do this up here so that I don't use up any of my space that I'll need for the rest of the problem. Whoops. So if we do our little product rule chart, if you will, we have x and then e to the negative x. The fact that you have two x's showing up in kind of completely separate pieces of the function should tell you that this is a product rule. So f prime will be 1 and g prime will be technically a small chain rule. It's also an e to the kx, but remember an e to the kx is technically a chain rule. So if I think of this as a chain rule, I would get e to the negative x. And then we would have to multiply by the derivative of the negative x, which would get us -1. The derivatives on this one are a little nasty, I'll be honest. So putting this together, we have f prime times g, so 1 times e to the negative x will give us e to the negative x, plus f times, I'm going to move that negative to the front of the e to the negative x. So we'll essentially get e to the negative x minus x e to the negative x minus. Now the next thing we're going to have to do is set that equal to 0. Now to make our lives easier for the algebra, trust me, notice that both of those terms have an e to the negative x in it. So we could factor it out. And that's always what I suggest you do. If there's a common term between all of the things, factor it out. So we would be left with 1 minus x if we factored that out. Because now we need to set it equal to 0. And we need to talk about if it's undefined. Let me talk about undefined first. If you look at this, you might not think there's a denominator, but there's actually a sneaky denominator here. Remember that a negative exponent would be a positive exponent in a denominator. So my e to the negative x could become a 1 over e to the x. So there's kind of like a sneaky denominator in this one. So I would need to ask, does e to the x ever equal 0? This super nice thing about e to the anything. Absolutely anything. It's always greater than 0. Maybe I should just use brackets instead of things that look like greater than symbols for my brackets here. So this is actually never going to happen. So once again, never undefined. Again, it's very rare that we would come across a function that's actually going to have an undefined derivative. But we need to consider it. So now if I jump back to finding this derivative being 0. Now I know that I just wrote that as a quotient, but I'm going to forget about that and just view it as this product of things. So since it's a product of things, I would set each piece equal to 0. Or if you want to view it as that quotient, you would just set the numerator equal to 0. You'll get the same answer. E to the negative x is never 0, because I just told you that e to the anything, and I mean anything, is always positive. Now, if there's negatives in front of the e, that changes things, but the thing in the exponent does not matter. And here we'll get that x equals 1 from that other piece. Now again, these ones get pretty long, so I'm going to pause for a second. Any questions so far? I'll wait like 5 seconds.
Do we have to do anything with the e to the negative x anymore, or because it never equals 0, do we just not work with that anymore?
I want to be careful with saying don't work with it anymore. It doesn't get us a critical point, but we are going to need to take that entire derivative later. So it's not like it can disappear, but it just didn't get us anything for the equals 0 part. But it can't like go away.
Okay, thank you.
So we've found our critical point, and we only found 1. So in this case, we only had 1 critical point. Sometimes you'll have more, sometimes you'll just have 1. So what do we do with that critical point? We plop it on a number line if we're doing the first derivative test. I'll talk about the second derivative test in a second if someone wanted to do that. We plop it on a number line. We pick some test points. Something less than 1, why not 0? Something greater than 1, why not 2? Let's not go too obnoxious. I mean, you can totally go as obnoxious as you want, but I plug both of those into the derivative. So if I plug in 0, I'd get e to the 0, 1 minus 0. If you want to think about it in terms of just the sign, remember e to the anything is positive. So here we'd have a positive times a positive. This would also just result in 1. So I plugged in 0, I got a positive value. E to the negative second, 1 minus 2. This would be a positive number times a negative number. So we should get a negative result. And if you're curious what the actual number is, because remember, you don't have to do that kind of sine way. You can always just punch it into a calculator. I'm running out of space. And write the actual number. So we get a negative result when we plug in 2. So if I do my little line segment pieces, that means that we would be increasing and then decreasing for the original function. So at x equals 1, we're going to have a local maximum. So we'll have a local max at x equals 1 and no local min. Let me box that. That's part of our answer. We're not done yet. Like I said, really long questions. but I'll pause there again. Any questions about that? Okay. So then we're essentially going to do the exact same idea, but with the second derivative instead. So now we have to find the second derivative. You have a couple choices now because we have a couple different forms of the first derivative. We could take the derivative of e to the negative x times 1 minus x. We could go back to this e to the negative x minus x e to the negative x. Whatever floats your boat. I'm going to use kind of this e to the negative x minus x e to the negative x. You'll get the same answer no matter which one you use. It's just a little bit of a different process depending on which one you pick. But I'm going to pick that one. Specifically because half of the work has already been done for me, and here's what I mean by that. So we want to find the derivative of this. So we have e to the negative x. So the derivative of that will be e to the negative x times negative 1. And then we're going to subtract the derivative of, now look at this, x e to the negative x. But that was my original function. So I already did the power rule for that. Sorry, product rule for that. That's exactly the product rule that I found up here. So the product rule for x e to the negative x have already worked out. And that turned out to be 1 times e to the negative x plus x times negative e to the negative x. Again, these derivatives are a little gross for this one. I will be quite honest. So we have negative e to the negative x minus e to the negative x because I have to distribute this negative. Now notice I'm distributing a negative into something that already has a negative in that last piece. So it will turn into plus x e to the negative x. And clean this up a little bit. I'll pause there for a second. Questions on how that came into being? Okay. One last thing we'll want to do for this to simplify it a little better. Trust me, it'll help in the next step. Notice we have negative e to the negative x minus e to the negative x. That's going to give us minus 2e to the negative x plus x e to the negative x. And just like last time, they both have an e to the negative x in them, so I can take it out. Okay. We've found the second derivative. I've written a little too large. I'm probably going to run out of space. But we found the second derivative. So now here's when we have to set that second derivative equal to 0 and ask if it's ever undefined. For the same reason as last time, this is never going to be undefined. Again, that's rarely ever going to be a case. But when we set it equal to 0, we essentially have those two pieces that we want to set equal to 0. Let me put a little bit more on this. Never same reason as f prime. So this will never happen because e to the anything is never 0. And then we get x equals 2. And some of y'all are like, how long is this frickin' problem? Very long. We're almost done. Plop that onto a second derivative number line, which is again why I like to label these, because now we have two number lines floating around in our problem. One of them uses the first derivative, the other one uses the second derivative. So find our test points, 0, 3. Yes, Jack, the exam on Thursday only covers up to 4.2 because we haven't talked about anything more than that. So we have to plug those into the second derivative. E to the 0, negative 2 plus 0 will be a positive negative, which will result in negative 2. E to the negative third, negative 2 plus 3 will result in a positive times a positive. Or if you just want to type in the number 0.05 if we round. So we have a negative on the left and a positive on the right. And I've run out of space. I mean, I'm pretty much done. I only have one tiny thing left to write, but gotta squeeze it in here a little bit. So we have an inflection point at x equals 2. Let me box that as well because I know this is getting to be a lot. And just to remind us of where our answers are. There's that. One tiny last thing I want to talk about really quick is if you had wanted to use the second derivative test instead of the first derivative test, say you were thinking to yourself, well, I'm going to find the second derivative anyway because I'm finding inflection points, so why don't I do the second derivative test? I don't have any space, but if you were to do the second derivative test, essentially what you would have done is you would have found the second derivative evaluated at 1, because remember the second derivative test is for extrema. So we would have found e to the negative first, negative 2 plus 1 is going to give us a negative number of, negative 0.367. Second derivative is negative, means that we'd be concave down, which would have gotten you that x equals 1 was a max. So you can sometimes skip that kind of first derivative number line if you want to use the second derivative test. But again, sometimes the second derivative test doesn't work. So sometimes it's just better just to bite the bullet and just use the first derivative test. I'll leave that up there for like a few more seconds. And then I'll erase the thing in blue. I'm not gonna like make it all go away. So I know that, oh my God, what have I done? So I know that that was a lot. Let me try to squeeze it all in here real quick. Are there any questions on anything that was in that example? Oh, my camera froze again. Okay. Someone in my other class asked how many of these will be on the exam. Since they are obviously obnoxiously long, there will only be one that does both of them. But there might be questions where it's like find whether this is a max or min or find the inflection point. But in terms of asking you to do both for one single question, for one single function, that wouldn't happen. Are the derivatives this messy on the exam? Not for like something like this. Like I might ask you a generic find the derivative question that was this quote unquote gross. But in terms of the ones for extrema or inflection points, no, it won't be this messy in terms of the derivative for that one. Could you have found the inflection points at the first derivative? That's a good question. I've actually never gotten that question before. No. So inflection points, you need the second derivative. So inflection points are where the derivative changes concavity. Now, well, in general, could you do it without the second derivative? Sure, you could, but it would be much more difficult than just finding the second derivative and doing the number line chart. I don't think I've ever seen someone do inflection points without the second derivative. I can technically think of a way that it would be possible, but it's just so much harder than it would be. It wouldn't be worth it. So no, to find inflection points, you do need the second derivative. Will problem 3 be on this upcoming exam? Oh, you mean like one we just did? David, yes, but the derivative won't be as messy. So it would be a bit more like this question 4, problem 4, where it's a polynomial instead of a product rule, but something like this where I ask you to find the extrema and the inflection points is fair game for the exam. How many questions are there on the exam? Some of these question types can be long, so there's not that many. There's 1, 2, 3, 4, 5, 6. That one has 3 parts, so 7, 8, 9, 3 parts, 10, 11, 12, 13, 14, 15 questions on the exam. You're welcome. I can totally do this last problem if no one has any other specific questions they want to talk about. But if anyone has any like different topics they want me to talk about really quick or whatever, I can go over that instead. I can put the answer for this up on Blackboard if we don't get to it. But I do want to just take some time to say, does anyone have any more questions than you've already asked about the upcoming exam? Anything you want me to go over really quick? Otherwise, I can go ahead and finish this problem 4 and finish up that one. I don't see anything else, so I'm gonna do this last one. Okay. Where'd my pen go? Here it is. Oh wait, sorry, Ben. What up?
Hey, will there be any multiple choice questions on the exam, or will it all be kind of written?
It's like last time where you have a couple multiple choice. There's going to be some of those find the error ones again. There's a couple of those in the review, so look at that to kind of see what I mean. So there's multiple choice, find the error, and free response. There's not as many multiple choices last time, but there are some. It's very similar setup to the first exam. Okay, I'm gonna do this one now. So again, oh, that kind of cut in. So let's redo that. So in terms of a question about this type of caliber on your exam, it would be something that's more like a polynomial like this than that product rule that we just dealt with. So let's do this one. I would say really quick, but these questions aren't quick. So here we go. So we want to find all extrema and inflection points. So first derivative, let me split this up again so I don't run out of space. So we'll have 15x to the 4th minus 15x squared. As always, I suggest you pull out the whatever common factors they have because it's going to make setting it equal to 0 easier. So they both have a 15 and an x squared in common, so we can pull that out. We'll be left with x squared minus 1. We need to set that equal to 0 and talk about if it's undefined. It's not undefined. Again, it's very rare, especially for the caliber of questions that we see in this class, to have that happen. But it needs to be considered. So since we have a product of things, we set those pieces equal to 0 separately. We'll get x equals 0, and x squared is 1, so we'll get x is plus or minus 1. So we have our first derivative number line. If we're doing the first derivative test, I actually think, if I remember correctly from my last class, one of my other classes, the second derivative actually fails here for one of the points. So you would have to go back and do the first derivative test anyway. but you wouldn't know that until you tried, but that's why I usually just default to the first derivative test, because that will always work. So we find some test points. We've got to plug them into our derivative. I'm moving. Oh, sorry, Anastasia, go ahead.
If we don't write f prime of x is never undefined on our exam for these problems, would we lose points?
Probably like half a point, but nothing like crazy. You should say something to me that tells me that you at least considered it.
Okay, thank you.
But doing something just like this, never undefined or something like that is fine. Yeah, because technically you should let me know that you considered it. So we have to plug all of these into the first derivative. We're kind of running short on time, so I'm going a little quick. So I think I'm just going to tell us what these numbers are, and hopefully I'll trust and believe me. Or you can punch them into your calculator and look at it later. So we've got 15 0.5 squared. 0.5 squared minus 1 will give us negative 2.8125. And so will the negative 1. That's just a coincidence. And then for 2, we will get 180, and for negative 2, we will also get 180. Also a coincidence. I'm going to assume that that hand is just still up, Anastasia, but if it's not, please feel free to interrupt me. Just like pop on and interrupt me, I don't care. So we have positive, negative, negative, positive. So we'll have increasing, decreasing, decreasing, increasing. Now, I personally kind of draw all the little line segments kind of on the same level, if you will. But if you like wanted to like keep decreasing just to like make it more visual for you, go right ahead. But I personally just like to keep it a bit kind of tight, if you will, to the number line. So the only time we change sign is at negative 1 and 1. So essentially 0 is going to be nothing here. It's not going to be a max or a min. So we're going to have a local max at x equals negative 1 and a local min at x equals positive 1. Oh, the lag is real. There we go. Questions, concerns on that half of the question? All right. So then we have to find inflection points. So we need the second derivative for inflection points. I would personally use, this unsimplified form to find the second derivative, because if you use the 15x squared times x squared minus 1, then you have to use a product rule and well. Whereas if you use the unsimplified term, it's just some power rules. So we'll get 15 times 4 is 60, x cubed minus 30x squared. Pull out what they have in common. They have a 30x to square. Sorry. That should be 30x, not 30x squared. They have a 30x in common. So pull out a 30x. You'll be left with 2x squared minus 1. We need to set it equal to 0, and we need to discuss if it's undefined. But that never happens. If you want, I can post an example of one where it actually does happen, but it's also a semi. The one example I thought of, because someone wanted me to send them one yesterday, I thought of one, but then it turned out to be massively uninteresting because there was no extrema. But anyway, so setting this equal to 0, we'd have those kind of two separate pieces being set equal to 0. We're going to have a kind of gross number in this one, but don't panic. So we're going to get x is 0. 2x squared is equal to 1. So x squared is equal to 1/2. So x is equal to positive or negative square root of 1/2. Should you technically reduce that a little bit, rationalize the denominator? Yeah, I guess so. But who cares? I don't. I care more about you knowing the calculus at this point than knowing how to rationalize the denominator for that. So you can totally leave it as the square root of 1/2. If you want to rationalize it, go right ahead. Or if you want to write it as a decimal, go right ahead. Whatever floats your boat. Once we found those points, we plop them on a number line. So we have the negative square root of 1/2, 0, and the positive square root of 1/2. For the sake of choosing our test points, we should probably view them somewhat as a decimal so we know what values we can choose. So the square root of 1/2 is approximately 0.707. So we've got to choose some test points. So why not 1/2, negative 1/2, I don't know, -2 and +2, why not? That one looks kind of gross. Plug them into the second derivative. And again, we're running a little short on time, so I'll just tell us what it is. What's my second derivative over on 60x cubed, 60x cubed minus 30x. Negative 7.5 for negative. No, sorry, that goes on positive 0.5. When we plug in positive 0.5, we get negative 7.5. When we plug in negative 0.5, we get positive 7.5. When we plug in -2, we get negative 420. And then positive 420 when we plug in positive 220. Remember, we don't really care about what the number is, we just care about the sign. So -2 gave us a negative, negative 0.5 gave us a positive, 0.5 gave us a negative, and positive 2 gave us a positive. Since I've run out of space on that side, I'm going to write the answer underneath my local max and min stuff, because then the answer will be all in one spot. Sorry about that. Doop, doop, doop. So for inflection points, we just care if it changes sign at all. We don't care about kind of the direction that it changes in, but it changes sign at absolutely all three of those points. So we will have inflection points at x equals 0 and both positive or negative square root of 1/2. And then we're done that one. Questions, concerns on that one, or questions, concerns at all, because now we're done. We've got technically 5 minutes left of class time, but I've got nothing else to talk about. So if you didn't get a question that you had in before, now would be the time to do it. Otherwise, if you're feeling comfortable, you don't have any questions, you're free to leave if you want. Again, we've only got 5 minutes left and I've got nothing else to talk about. But if anyone's got any questions, feel free to ask them.
How'd you get an inflection point at 0?
Because the second derivative still changed sign there. Remember, we don't care about if it's negative to positive or positive to negative. As long as it changes sign at all, it's an inflection point. So the fact that to the left of 0, it's negative, and to the right of 0, sorry, I said it backwards. To the left of 0, it's positive, and to the right of 0, it's negative. It changed sign, so it's an inflection point. I'll stick around for, well, I'll wait till the end of class time. And if there's no more questions by then I'll just awkwardly leave. But if you have questions, feel free.
I have a very specific question, but on problem 4, when you were finding the values for f double prime of the points where f double prime equaled 0, or the x equaled 0, so like -2, -1/2, 1/2, and 1/2. How did you get those values? Because when I'm plugging the same things into my calculator, I was getting completely different values and different signs too.
You're a strange, weird calculator, Anastasia. I don't know what's going on with you.
Yeah, I don't know what's wrong with it.
Let's see. One thing that I can think of that might be happening. So when you're typing in the cubic part, so we're using 60x cubed minus 30x, right? At least that's what I was using.
Oh, okay.
Are you using the factored form?
Yeah, but I'll see if I get the same answer when I do it that way.
Well, so I think it might be the same issue either way, if it is this issue that I'm thinking of. So one thing, factored form or not, when you're putting it into, especially the negatives, the -2 and the -0.5. So say you're plugging it into the factored form, make sure that goes in parentheses. Were you putting that in parentheses with the power on the outside of the parentheses?
Yes, I was. But now that I plugged it into the 60x cubed, it's I got the same values as you did. So
I do something.
Problem solved, I guess.
No, I don't think that's the solution.
Okay.
Let me see. Let me see. I plugged in -0.5 to the factored form and I got what I got. If I plugged in positive 0.5, I get what I got. Without seeing what you typed in, it's hard for me to figure out what went wrong. But when I used the factored form, yeah, all of mine came out to be what they should have been. And if you're doing the parentheses right, do you have an old, what type of calculator do you have? You have a 84, right?
I have a TI-84.
Huh. So actually, do I have this on this computer? I forget. Oh my gosh, so many things are open. I do. Let me pull up my little fancy thing. And let me share my fancy thing. It's so fancy. So let me demonstrate what like one of them should look like. So did you have something like 30 times -2 and then times, what am I doing? Negative, nope. Then we would, go over, and then we would have to do -2 all squared minus 1. Whoa, what happened? Did I oh, because I didn't, oh, it's 2 times, right, hold on. Hold, please. There's a 2 in front of this. I know I was missing something. Booshki. Did you type in something that looks like this, or what? How did you type it in? Let me ask you that.
Yeah, I typed it in just like that, and even when we were doing that problem before, I still was getting the wrong value.
Anastasia, Calculator is possessed.
Yeah. Okay, I guess I'm gonna have to figure out a new calculator then.
So like just like this is how you type. I don't know what could have
Yeah.
gone wrong there. So Anastasia, here's what to do for the exam. Even if you use your strange possessed calculator, make sure you write out as much work, as possible. So, well, I should be clear what I mean by that. Where's the thing that I want now? So if you were doing one of these on the exam, make sure you've written out something like this so I can see what you were plugging in and what you got. And even if your numbers are off, I'll at least know that that's where the offness came from. And things can go better. The more work you show me, the better it's going to be. Even if your calculator's, I don't know what's wrong with your calculator, Anastasia. But
Okay, so if I wrote out on my exam and instead of doing like f prime of -2 equals and then whatever my calculator put, if I wrote out the whole equation and then plugged in the -2, would you give me full credit even if I got the wrong answer?
So if you wrote it out in that much fullness, I would probably not take off points because I would see that you have the setup right. And as long as like the answer that you get is correct based off of what you have, like even if your signs were off, if you at least then found the answer correctly for those incorrect signs, if that makes any sense, then it'd be fine. Because your calculator's just been giving you some real hard trouble. I don't know what's going on there.
Okay, awesome. Thank you so much.
You're welcome. All right, I'm going to stop the recording. We're technically officially out of time, but if anyone's got